Alright everybody, the next section is about vectors in the plane. It's another doozy of a section. It's going to be definitely a two-parter. I mean, I'm just going to power through like I usually do and just make one long video. But if you want to do the same, all the more power to you. But if you want to break this up into two sittings or something, then that's obviously also fine. It's potentially a really long video, I'm literally making it right now. I don't know how long it's going to be exactly, but I think it's going to be kind of long. Now there will be, as new as this sort of topic might be to some of you, or maybe all of you. I mean, you talk about this in physics, I think, like vectors and stuff. But anyway, the point is, like, there are certain pages of this flip chart presentation that I can probably just sprint right through and not really linger on those questions or pages really for very long at all. But it's a video, right? I mean, you could go through this video at your own pace. You could go back and watch parts that I might have gone a little too fast on, pause it and look at the work, whatever. But anyway, here we go. So an object moving along a straight line, and let's just, for our intents and purposes, let's consider this like literally a horizontal line. So if you have an object that is only able to move along like a horizontal straight line, that's only two directions, left and right, if we were going with like a horizontal line. And you only need one number to represent its velocity and direction. You just need one number. If you talk about what's the velocity of this object, you only need one number, and the number describes the velocity, or how fast it's going, and whether it's positive or negative discusses what the direction is. Negative, it's going, I guess, left, quote unquote, and positive velocity be going to the right. Okay? Now, if an object was moving in a plane, now there's infinite directions. Up, down, left, right, this diagonal, this angle, blah, blah, blah. There's infinite number of directions an object can be moving in a two-dimensional plane. The velocity and direction can be represented by two numbers, just like points. Just like coordinates of a point in the xy plane, velocity and direction of a object can be represented by two numbers. So this is just kind of just showing, like, this is old school since, I don't know, 5th grade or 4th grade, or I don't know when you first started plotting points. But you can sort of use the concept of, coordinates to talk about how, if you were starting from the origin anyway, which, whatever, might as well, that's going to be a big thing, you could use coordinates to describe the direction of the object's movement, right? From, again, especially if you're going from here, right? And also the velocity, because of the length of this vector arrow. So the velocity would be like the length of the arrow. And notice the special notation that we're going to be using, like these, I don't even know what they're called. They're obviously not brackets or parentheses. I don't even know if they have a name, but these, like, arrow type symbols for grouping. So, two-dimensional vectors. Let's kind of breeze through this. A two-dimensional vector, v, is an ordered pair of real numbers denoted in component form as that. So there it is. There's component form with those special grouping symbols for vectors. The numbers a and b are the components. The blank blank of the vector is the standard form. The standard representation of the vector AB is the arrow from the origin to the point AB. So standard representation coming from the origin. Standard representation of a vector is the arrow from the origin to the point AB, like, literally in the XY plane. Again, I'm moving on, man. I don't want this video to last 5 hours. It won't, but again, pause, write down notes, whatever. The magnitude of a vector, or absolute value of v, denoted, well, that's not a surprise. The magnitude, which is pretty much absolute value, okay, of a vector, is denoted with absolute value symbols. Yay, okay, that's good. Is the length of the arrow. That's what I said. Is this like a formula for it then? Okay, so how would we calculate? I mean, I'm assuming it is, so this will be embarrassing if it's not even. But how do we calculate the length of an arrow like this? How do we calculate it? What is the length of this general arrow, considering, the coordinates of this point right here, and that 0, 0 would be AB. Wouldn't this be like wouldn't this be like a Pythagorean theorem type thing? Yeah, think about it. This is essentially the Pythagorean theorem. It's the length of a hypotenuse, basically. So yeah, nothing new, right? Nothing crazy. The absolute value, the magnitude, is basically using the Pythagorean theorem. So keep that in mind, okay? The zero vector, well, okay, that's probably not too shocking that this would be, it's almost like a vector you can't even see. It's like a dot, I don't know. The zero vector, right? I mean, some arrow that is. And then, okay, a little more pre-calculus coming up. A little more trigonometry. The direction angle of a non-zero vector is the smallest non-negative angle formed with the positive x-axis. So in this situation, the direction angle of a vector would be, right here, whatever is in between the vector and the positive x-axis. Alright? Smallest non-negative angle formed with the positive x-axis. Alright, now the head minus tail rule. Now what this sort of relates to is, I mean, you don't have to have a vector starting at the origin, duh. I mean, right? That'd be kind of weird. So if you have some random vector that starts at some random spot and ends at some whatever other spot, that's not the origin, the starting point, you can, like, what's the word? You can almost like rewrite it in terms of like the same vector, but it would start at the origin. So like if you took this vector and you literally just moved it so that the starting point was the origin, then how can you describe it? And so I don't think it would take too long to think about the mathematics here, how you take like, you know, this component, this x coordinate basically, minus this other component or x coordinate to get like, the final component where, it's the same arrow with the same length and the same direction, but now it's starting at the origin. So again, keep this in mind, that all you do is you subtract the two x coordinates and you subtract the two y coordinates to get like, the standard representation, remember, standard representation of that vector. Okay, where it would, again, I know I've said this like 3 or 4 times already, but the vector that would start at 0, 0, the origin. So head minus tail rule. Quick example. Once again, especially like pretty much the entire quote-unquote part 1, I don't think is going to cause you guys any issues like at all, except for like maybe shaking off a little rust from how long ago you learned trigonometry in pre-calculus. But okay, here's this example. Let's see. Find the magnitude and direction angle theta of this vector. Find the magnitude and the direction angle, right? Well, I mean, think about it. This is the standard representation. So once again, finding the magnitude, and look, drawing a picture is probably a good idea. Drawing a picture is a good idea, especially when it comes to like the angle, because remember the angle, the direction angle, has to be formed with the positive x-axis, not just the x-axis, the positive x-axis. So a little, again, pre-calculus, but the magnitude is just basically going to be the, oh, what in the heck? Oh my goodness, I have a little typo here. Well, I don't know if it's a typo. When I was, ooh, good thing I noticed this. When I was making this all fancy like, speaking of fancy, let's when I was making this all purty, I think I forgot to also pretty up the woo! I'm gonna have to anyway, yep. So it's the Pythagorean theorem, and so when you let that play out like you've done 100 times before, you end up with a magnitude of 2. Like, so if this vector was describing a velocity, the velocity would literally be 2 feet per second, 2 miles per hour, whatever. Now the reference, well, the direction angle, right? You have the pre-calculus chops somewhere in the back of your head to be able to figure out what this angle would be or something, because what would this be like? 1, 2 square root of 3, 1, 2 square root of 3 as just a triangle. I know it's negative 1. 1, 2 square root of 3. So wouldn't this angle, which is across from the root 3, wouldn't that be 60 degrees? Yeah. And so if this is 60 degrees, and again, remember, the direction angle is with the positive x-axis. So if that's 60, then this should be, of course, 120. 120 degrees. Easy. Find the component form of a vector that has a magnitude of 3. So now we got to find the actual vector, the component form of it, the a comma b, so to speak, with a magnitude of 3 and a direction angle of 40 degrees. So essentially we want, again, drawing a picture's good. And we just want to find, like I said, Sorry, I was thinking about something else really quick about my time constraints. I'm actually on a time constraint right now making this video. I might end up actually stopping after part one, as like a calling an audible type thing. But anyway, so what we need is like the coordinates, the a comma b, or the x comma y. So again, that's trigonometry. If we know this angle is 40 and we know the hypotenuse is 3, I assume we're going to find x first, or a, yeah, I mean, same thing. Knowing the hypotenuse, and we need the adjacent leg. To me, that's going to be cosine. Remember how SOHCAHTOA, remember how the cosine is equal to adjacent over hypotenuse? So, using a little basic trigonometry, in other words, the cosine of 40 is equal to a over 3 because of SOHCAHTOA. And then likewise with the b value, this y coordinate, so to speak, and that would involve sine because sine is opposite leg over hypotenuse. And so you just grab a calculator and, boom, bam. So this would be like the approximated, anyway, with the approximate values, component form of this vector, right? That's, so again, more basic trigonometry. And then we have some vector operations, right? These are going to be pretty easy. I'm just saying. So let u be some vector with its components. Okay, just don't get confused by how many uses of like subscripts are being thrown at you, starting pretty much now. So we have a u vector with its obvious a, b components, and then we have another vector, a v vector, and let k be some real number. And I don't know if you ever learned about matrices, and you've done stuff with matrices, but what I'm saying is you might recognize this math word of a scalar, but it's just some regular real number. Okay, no big whoop. The sum, all right, the SUM sum, or resultant of the two vectors is, of course, right, this vector. So again, it's very clear and like expected what happens. Okay, like if you just add the vectors together, this is all you do. You add the corresponding components together. Now, picture-wise, I know this could be a little bit overwhelming to look at as it's like as a finished product, but check this out. Let me move that for a second. So the u vector and the v vectors, the v vector, completely separate, and when you define them like this, they're starting at the origin. If you add them together, you get the purple vector. Adding these vectors together, the resultant vector, you're going to get the purple vector, and that's why. Like if you kind of just start the blue vector right where the red vector sort of left off, and likewise you could do it the other way, blue to red, whatever. That's pretty much the picture representation of adding two vectors together. It's new, probably, and a little weird to some of you, but not all that, mind warping or whatever. The opposite of a vector v is just literally negative v, or -1 times the vector, which we'll look at, I think it'll all come full circle kind of down here, like multiplying -1 to a vector, I mean, it's going to be exactly what you might expect. And then, so this is how we define vector subtraction. I mean, we're kind of making a mountain out of a molehill here, but adding vectors, you'd think you could just, I mean, and yeah, you can, but again, we're kind of making this a little more complicated than it needs to be, but, technically subtracting vectors is adding the opposite of vector v. And then as far as like the product of a scalar k and a vector is exactly what you might expect. We're just going to multiply that scalar to each separate component. So easy, super easy, super easy. And then if you wanted to kind of have like sort of a visual representation, okay, sort of like a graphical perspective, if this was, say, your vector u, right, kind of going up like this at this angle, whatever, this length, this magnitude, then this would be 2 times u. This vector would be a picture of what 1/2 times u looks like. And this, people, would be a picture, look at where the arrowhead got switched to. This would be a representation of what -2 times u would look like. Fascinating. And I feel like I can definitely, I mean, that was easy enough, not to, I mean, I don't want to insult anybody here, but hey, I didn't think it was that easy. You will, just give it a little bit of time. I mean, the point is, I think I can really sprint through the next handful of pages. These examples should not give you that much trouble, especially, after you get a little bit of practice and put a little bit of time. So if that's vector u and that's vector v, then what would this be? 2 times the u vector plus 3 times the v vector. Well, the first thing you do is you multiply the scalars. Okay, this is like second grade back. And then you add the corresponding components together. Okay, again, I'm flying here. If you need to pause or whatever. Now, what about u minus v? Well, again, technically, not to make this more complicated than it needs to be, but technically you're adding the opposite of v, and you're first multiplying -1 to the v vector, and then adding, remember, subtracting is really adding, you're adding the opposite, and so then you add these corresponding components, and boom, bam. And then, remember, people, what does this mean? These lines, obviously, you recognize as absolute value. Do you remember precisely what absolute value of a vector means? It's the same as magnitude, with which means the length of the arrow. So absolute value of a vector is essentially the length of the arrow. And so we're going to, at least at the end of the day, by the time this is all done, we're going to have to use basically the Pythagorean theorem. Magnitude, which makes you think of community. Magnitude's a one-man party, and a one-man party can't be in an alliance. That's a paradox. I agree to disagree. Easy there, paradox. Sorry. Magna. So here, back on track. So maybe we first find out what 1/2 u is. Well, I guess we'll keep the symbols, but so multiplying 1/2 to the u vector, we get -1/2, comma 3/2. And then now you just have to take the magnitude. All right. And that, again, like I said, that requires essentially doing the Pythagorean theorem and finding the length of the hypotenuse. And, we doing this by hand, basically. What would this be, like negative? No, not negative. It'd be positive, idiot. Positive 1/4 plus positive 9/4. Yeah. Positive, the square root, of course, of 10/4. And why is there one more box in right here? Well, because can't we at least take a clean square root of the denominator? Remember, you can break this fraction up into like separate square roots. You can separate square roots by division, right? And so you can write a final answer of root 10 over 2. Okay. Now, full disclosure here, people. I kind of wanted to just power through and make one long video, but part 1 here took about 25, maybe between 25 and 30 minutes. Not 30 minutes, but whatever, close to it, I guess. At least 25 minutes. And so that's not a very good sign, so that leads me to believe that part 2 is going to take, a bit longer than that. And I actually have a like a faculty conference call meeting with Mr. Rimpa here in a half hour. So I'm going to stop here, and so this section will be basically broken up into 2 videos. But if you just want to power through, right? Because part one wasn't really that heavy, was it? Some pre-calc flashbacks, but you totally might want to just kind of click on the next video and kind of power on through part 2. I'll catch you on the flippity flop.